Greeting professors. Um, this is my presentation for the CSCI 331 Operating System Project 1. My name is Sing Hyun. So for this project, we'll be comparing the performance of the process creation and destruction using a linked list and without the linked list. So I've implemented the project in C++ programming. So here, it's just the basic library, the OS stream and the chrono for recording our uh, starting time and ending time for our processes. So here it's just I've set a maximum of PCB array size for our later implementation. So for our first version, we have two data structure. So our first structure is a child node. And in this child node, we have two fields. So the first field is children index. So to just record our children index. And the second field is just a you can think of it as like the pointers to the next node or the next struct. And here is just our constructor, basically just initializing our two fields that needed values. So here it's just null pointers because we will utilize that for later. So in our next structure for basically this is like our PCB parents. So we have two fields as well, our parents index and then our children. So we can think of this as like the head, like the head node of our linked list. And here we're just it's just a simple constructor initializing the value needed. So here's our implementation for our classes. So this is just initializing our array, our PCB array, which has the size of 1000 if I mentioned the above. Here is just a simple constructor. We need a first we need one available parent first before like creating any other children. So here is our creation function. So what does this line particular do is just to find available spaces within our PCB array and then initialize that. So if we run through our array like from 1 to 1000 and we still like q isn't initialized to any like value within like I, then we'll just return -1 as like an indication of the PCB array is full. So afterward, this is just we're initializing the children. So our children is Q and our parents is P. So we're just setting our children parents to Q, to P, I apologize, and our Q children to null pointer for its next children. So here we're creating a node using the child node struct. So we can basically initialize our children of P, like the fields, because our P parents still doesn't have any children initialized yet. So this is just we're basically measuring whether it's available or it's not. So if it's equal to null pointers, then it's available. We can just initialize that node. So if it's not, then it's the second condition where we have to iterate through the P parent children's. So basically this is just iterating through till the end, or we can say we're finding the tails of our parents PCB. So once we found that, we can just initialize the next children to be that node. I mean the tail children next field to be the node. So here we're just returning Q if it's a successful creation. So here it's a destroying function. So basically it's a recursive function that destroy the process's children and then setting the parents to be available. So here you can think of it as the head again, the head of the PCBP parent. And then we're just basically iterating through from the head to the tail, and then basically just destroying and making it available for the next perhaps iteration. So here is our second version. Our second version, we're basically just creating with only 4 fields. We don't use any linked list. So we have the parents, first children, younger siblings, and older siblings. And this is just the basic constructor. So let's look at the implementation. So this is the same thing. And this basically this part is the same, and so is this one. It's basically we're just finding available spots for our new children. So once we do, we just initialize our basically our children Q, and then initialize its parent to have P value. And everything else is still -1 for future use. So here, if um if the P parents doesn't have the first child yet, we can still think of it as like the head node. If it doesn't have any head nodes, which equivalent to -1, then we can just initialize Q to that. But if it does, same iteration as before, we basically iterate through our heads to find the tail. And our tail will be the kern. So first we have to initialize the younger sibling of our kerns to have the value of our new children Q, which will be the youngest. And then we can initialize the Q older sibling field to have the current. Afterward, we just return Q, basically the same thing for a successful creation. So here it's just another function for destroying our children of the parents as well as freeing up the parent space. So here is the same thing. We're just taking the heads and then we iterate through and then destroying all the children and then setting everything to -1 to free up space. So here's our test program. So I've initialized the iteration to be 1000. And here we basically allocate some space for our H1. And then we record the time. So start one basically just record the timing before like it start the iteration or the process execution. So it will iterate from 0 to our 1000, our set value, basically creating all these childrens and then destroying the children afterwards. And after all the 1000 iteration, we will record the stop time. This will be useful later, and then we do the same thing for our second version. So once we get both the start time and stop time for both versions, then we can calculate and find the time that it has taken to process all of this creation and this destruction. So this is just like printing out how long it takes per each version and then the time that we have saved. So let me run the program. Here we can save around 123 microseconds. So that's a very huge difference. And this is the end of my presentation. Thank you.